Okay, our last lecture stopped at slide number 59, right? Okay, so before we continue, okay, we discuss, let us recall types of filters. Okay, so basically there are 4 types of filters. The low pass, which allows any signals smaller than the cutoff frequencies, whereas the high pass allows the signals to pass through any frequencies above the cutoff frequencies. And the pass band or the band pass filter allows the signals to pass through between 2 cutoff frequencies. Okay, and the last type of signal, the 4th one, is the stop band filter, which allows only a certain range of frequencies between the low cutoff frequency and the high cutoff frequencies. Okay, so last week we did an examples on one frequencies. This is a low pass filter. Okay, we did the calculation. Okay, and okay, when we have the other example, 14.11 is the band stop filter. When you measure across, okay, remember I mentioned determination of the filter depends on where you measure the output. So if you measure the output across capacitor and inductor, the circuit becomes a band pass filter, because when you measure across for a series circuit, series RLC, if you measure across the resistor, you're going to get a low pass filter. But if you measure across the capacitor only, you will get a high pass. And if you measure across inductor and capacitor, because the inductor can introduce a cut-off frequencies, it will combine so that it becomes a low pass and a high pass performance, and then the overall effect will become a band pass filter, which allows only within certain range of frequencies. Okay. Okay, have you done this example? I'm not sure whether, I think this one is not finished yet. Okay, so this one, you are given the resistor has 150 kilo ohms and reject frequency of the band stop filter is 200 hertz. You are to find what is the required value of inductor if inductor and capacitor if this resistor is 150 kilo ohms, and given the bandwidth of this band stop filter is 100 hertz. So you can use the equation for resonant frequency, okay, and given a bandwidth, we can obtain the low cutoff, the half power frequency, which is you divide by 2, B bandwidth is equals to twice the resonant value, which is 2 times omega naught. And if you plug in the value, so you will obtain omega naught is the 100 hertz. We consider the resonant frequency as the bandwidth. Therefore, we will get the bandwidth will be 2 times the 100, is going to be 200 pi radian per second. Okay. From this, you can calculate the inductance, because bandwidth is always equals to R over L for series circuit. Okay, and therefore your L is going to be the resistor of the circuit divided by the bandwidth of the circuit. And from here you will have 200 divided by 150 divided by 200 lah, 200 pi. And you will obtain 0.2387 Henry. Okay, since to find the capacitor, you can use the equation for the resonant frequency omega naught is equals to 1 over set of LC. So you have the value of inductor L. So you can manipulate the equation, make this capacitor as the title of the equation, and you will obtain C is equal to 1 over omega naught squared times L. And this gives you 2.653 microfarad. Okay, so from here you will be able to calculate the required capacitor and inductor in order to make the circuit having a bandwidth of 100 Hertz. And the reject frequency is at 200 Hertz. Okay, and if you change the value of capacitor and inductor, it will change the bandwidth, and it will also change the reject frequency. Okay, so the value of the capacitor and the inductor, as well as the value of the resistor, will determine the cut-off frequencies, the bandwidth, and also you can calculate for the Q factor for the circuit. Because a filter has its own performance, and you will have a quality factor for each of the circuit. Okay, so to do more, you can do, to explore more, you can do on your own the practice problem 14.11 from the textbooks. Okay, I move on with another example. What happens if we have one series, we are evaluating series RLC. Depending on where the output is taken, this circuit can produce a low pass, high pass, or band pass, or even band reject filter, which is the band stop filter lah. Okay, if you measure across the resistor, okay, we apply input across RLC, and if you measure between the ground and the resistor, only at this section you will see a band pass filter. But if you measure from the ground to the inductor, okay, sorry, from capacitor to inductor, between two elements here, you will obtain band reject filter. And the equations, you always can relate the output to input, and you will have this equation where you have VL over VS, because VL is the output side, VS is the input side, and you will obtain, we can consider during omega equals to 0, the signal will be 0 because there is no output lah. And when you have omega equals to infinity, omega is the frequency, very high frequency, you will have the VL is equivalent to VS. So therefore, the VL over VS becomes 1. For the omega equals to 0, which is DC condition, the VL is 0. So 0 over something, you get 0. That's why you have 0 performance, 0 value of output when low frequency. So omega equals to 0 means DC lah, DC behavior. So from here, it shows the high pass performance because anything above a certain, so let's put if omega is not the infinity value, some value, so anything above that value, you will have an output of 1, means the ratio will multiply with the multiplier magnitude of the output. Okay, for V, when you measure across VC over Vs, the equation will be 1 over j omega divided with 1 plus j omega minus 1 over omega c. And when low frequency DC signal, a capacitor can allow very low frequency, it produce output of 1. But when very high frequency, omega is equals to infinity, the signal become 0. VC is equals to 0. Therefore, the output VC over Vs is 0. But this one is opposite to this inductor output. So therefore, this one is actually behavior of a low pass because you consider anything omega not, omega, the frequency, less than the certain cutoff value. Okay, so if you do the simple plotting comparing the behavior across the capacitor, inductor, and so on. So this blue line, a blue curve. So you have here VC, anything below than this cutoff. So you take this one as cutoff. So you will have this as a low pass response. But for inductor, anything below it, below a cutoff is 0, but above it is going to be a value of 1. And so you will see capacitor has opposite behavior compared to the inductor. So for resistor's behavior, it is the bandpass response because for capacitor, resistor, when you measure the output across the resistor, you will have the band pass filter performance because it's combination of the capacitor and the inductor. Okay, so the key point for a filter very much depends on where you measure the output, and this is very true for series circuit. For parallel circuits, normally it's obvious. It does not matter how very much on where you measure, because when you have a parallel capacitor, you can have resistor, and depends on the other components, especially. Okay, and okay, the active filters for the from the textbook is not covered because the active filters is op-amp circuits. However, later on you will need to use it. Passive filters have few drawbacks. They cannot create gain greater than 1. Okay, they do not work well for frequencies below the audio range. They require inductors, which tend to be bulky and more expensive than other components. It is possible that using op-amps to create all the common filters, because an op-amp filter, you can have amplification behavior. At the same time, you have the process of filtering. Okay, but for passive filter, passive means you are using passive components, the resistor, capacitor, and inductor. There is the output will be always less than 1 of, which means if you apply input signal of 5 volts, for example, you will never get the output more than 5. Definitely you will, when you measure the output across the section that you want to measure the output will be less than the 5 volts. Okay, I suppose you have one lab on frequency response with Dr. Gan, if I'm not mistaken. But I think the lab is delayed because of this pandemic. And if you do the experiments, physical experiment, you will have the experience of measuring the output. You just measure the output after you vary the frequency. So you are not paying attention and too much on the magnitude of the signal. You just want to make sure on what is the effect of the frequency. Okay, at which frequency the signals attenuated very much. Attenuated means drop in terms of its magnitude compared to the input signals. So if you do most of the time in the lab, you apply very small input. Normally we use 5 volts, and then you look at the output at which frequency. So if you have a low pass filter, you would expect below certain cutoff frequencies, the signal is almost, output is almost 5 volts. But above the cutoff frequency, slightly above, you will have a drop of less than 5, but far above the cutoff frequency, you will get an output of 0 later on. Okay, but without the physical experiment, using the simulation, you can also evaluate the performance of the filters. Okay, so however, in the lab, we do not test on active filters, not in this course, but in electronic analog next semester, you will deal a lot with op-amp. Okay, so later on you know that the op-amp is a circuit, integrated circuit that amplify the signals. So you apply very small signal, millivolt signals, but you will get few volts output. So you can have an amplification factor of few hundreds. Sometimes you may have 1000 gain. Okay, and another thing about the active filters, this on top of amplification, it also can isolate the input and output. Its ability to isolate the input and output so that it makes a very improved performance. Okay. So although it's not covered, because I have put some one question in the mini project, bonus task. So let me introduce to you all roughly on basic of active filters. Okay, for active filters, the symbol triangle like this is the op-amp circuit. So to make this op-amp circuit an active filter, normally an op-amp, you introduce one resistor from output to the input. An op-amp has two inputs, the negative input terminals and the positive input terminals. And normally the negative terminal is grounded. So later on in your electronic circuits, you will learn there are many ways to connect the op-amp circuits. You can make inverting amplifier, non-inverting, unity gain. So that I'm not going to touch on that. But for this one, for this circuit theory 2, I just introduce you all how you can make the op-amp as basic low pass, high pass, band pass filter, and the band stop filter. So normally for a filter, we connect it as an inverting performance. This is an inverting behavior because you connect the input to the negative terminal, and this RF, the feedback resistor that connects from the output to the input, and you introduce one capacitor which is parallel to the feedback resistor. So when you see capacitor in the feedback, the filter becomes a low pass filter. But if you replace the feedback resistor with parallel RL, the amplifier becomes a low pass filter. And the corner frequency will be, corner means a cut off frequencies, omega C equals to 1 over RC. For high pass filter, the capacitor here, you put in the input section, and the feedback only RF connect the output to the input side, and the cutoff is again 1 over RC. The only difference between the high pass and low pass filter, for this circuit, frequencies higher than this omega C will be allowed, but frequencies below the omega C will be attenuated. But for this one, because it is a low pass filter, frequencies below than this omega C will be allowed. Frequencies above this omega C will be truncated or attenuated. Okay, for band pass filter, using the active filters, we can simply make into stage by stage filter, where we introduce low pass filter, high pass filter, and inverter, and so you introduce stage by stage to avoid the use of an inductor, because inductor is very seldom used. Capacitor is more common. It is possible to use a cascaded series of low pass active filters into a high pass active filters. To prevent the unwanted signals passing, their gains are set to unity with a final stage for amplification. Unity means the gain of 1. Okay. And remember, for actual performance of filter, the cutoff is always taken at 0.707 of the maximum gain. Okay, band reject frequency. You can also do a series cascade system. However, the difference between band reject filter and band pass filter, you do a parallel low pass and high pass filter, then you do a summing amplifier, then you will have this band reject filter. Okay, creating a band stop filter requires using a low pass and high pass filter in parallel. Both output are fed into a summing amplifier. It will function by amplifying the desired signals compared to the signal to be rejected. So compare here, you have a series system, series, or you call it cascade lah. But this one you have parallel system. You apply input, one input to the low pass, another input to the high pass, and then you sum up those two output from this stage filters. From there, you will obtain the out of band stop filter. Okay. Basically, that's about the topics to be covered in this chapter. And regarding the project, okay, I have upload the task sheets, materials, and also PSpice installer. Okay, here I put for June, but in the actual task sheet, I consider for June is too soon. So I gave more time. The due date is 8th of June. So let me change this one. Okay, and okay, the grouping. Okay, if you notice, okay, I have combined students. You should work in pairs, and total number of students this semester is 132. So that makes 66 groups. So each of you all are given the task sheet itself is actually for student to simulate. Okay, let me see the task sheet. Okay, here I put at 8 June. Okay. Okay, I put instructions here. You have to do the simulation using PSpice, and I have provide PSpice installer. I have upload all those important links in UKM folio. And if you are not familiar with PSpice, I state clearly here, students are also allowed to use other simulation software such as Multisim, Tina, or other software that they are familiar to complete the project. So those who are not having, I suppose, because you have had CAD-CAM last semester, right? In CAD-CAM, you learn few softwares. So you can choose whatever software that you like in order to simulate any electronic circuits. Okay, so the task is for you all to simulate, and then these are the instructions here for PSpice. Now, if using PSpice, these are the instructions how you can do in schematics and do the magnitude plot using the PSpice. But using other software, I'm not sure. So you can explore that. So you have to do magnitude plot and phase plot for the body plots. Okay, the main task of the project is to evaluate only one of the circuits from the figure 1. Okay, and this figure 1 actually consists of, here you have figure 1, figure 1A, 1B, 1C, 1D. So when you look at your the project distribution, project student grouping, so like the group 1 is to simulate circuit A. Group 2 is to simulate circuit B, circuit C, and D, and so on. So I will have like 16 sets of circuit A, B, C, and D all together. So if you look, I only use simple series RLC and look at where you measure. So from here you can guess, but you can also confirm your guess regarding the type of the filters, because these are all filter circuits. So when using the simulator, from your simulation, you can see actually whether your theoretical guess is true or not. Okay, so from here although the task is simulation activity, I still want students to evaluate the circuit theoretically. So that means you are to do manual analysis of the circuit. So for the manual analysis, you need to calculate the bandwidth of the filters, Q factor, lower and upper cutoff frequencies, respectively lah. If the circuit is low pass filter or high pass filter, you only have one cutoff frequency. But if you are assigned, that your circuit, the given circuit is a band pass filter or band stop filter, there are two cutoff frequencies lah, the lower cutoff and the upper cutoff frequencies. So for the manual analysis, you need to show your calculation, and you do your sketching of the magnitude and phase plots to make up the body plots. And also you need to show the transfer function of the circuit. So these are all manual analysis. Okay, and then the simulation, you need to show the constructed circuits, meaning that you copy and paste, or you save your figure that you from your simulation software, and then you produce the magnitude and phase plots using the simulation software and insert into your report. So there are two parts of the project: manual analysis and simulation analysis. Okay, so send a copy of report through the UKM folio. So if I'm not mistaken, let me see, where is mine? I have put everything. Okay, login. Okay, chapter 14. Oh, tomorrow you have exam. Okay, that's why I plan not to proceed with the next chapter, because I will allow you time for the preparation for the exam. Your exam is 2 to 4, but half an hour is reserved for uploading. So don't forget to complete your student declaration form, feedback declaration form. Must be completed before taking the exam. That is your midterm. Okay, so for chapter 14, I've uploaded a link to the lectures on 20 May and also on 25th May. Okay, so I upload already the mini project and link for the PSpice installer. Okay, the submission, I put the submission tab So you must submit through UKM Folio. Do not email, because it's very difficult to organize files received from emails. From the UKM Folio, the system will organize very well according to the student name. Okay, and all right. What else that? Okay, the other thing is just for you all to the project. This one is general. This one is how you want to install, what to do with the installer, and brief report. Okay. Please name your file, your report file as group number. Okay, group number, and then ID student 1 and ID student 2. So in front of the cover, you have to put the detail of student ID and name lah on your front cover. But the file should be always start with group number, so that I can arrange the files systematically based on student file numbering. Okay, I think that's all for today. So we finish very early. So any questions regarding anything regarding the project or regarding?
Doctor, the list of formula about exam will be given, right?
Not sure. I was
so
not
we have to
informed.
remember lah. Oh, what?
Yeah, most of the time, for circuit theory, we do not give formulas because it's a understanding of the concepts. But I'm not sure. You can ask Dr. Wan Mimi and Dr. Badaria whether a specific formula is given. Okay, last semester, similar to last semester lah actually. You can ask via Teams, Microsoft Teams. Just post a questions, or you can send chat message, so they will answer. Okay, so it's tomorrow, yeah, tomorrow afternoon. Let me go to.
Excuse me, doctor.
Yeah.
I want to ask about bonus task. We don't need to do the manual analysis, right? Only PSpice for bonus task.
For bonus part, you just simulate and then no need to evaluate in terms of manual, or you can present the simulated version as a proof that you have simulate. That's all. Because the reason I put a bonus question is for you to experience dealing with active filters.
So just attach the results, the board plot, only the board plot.
Body plot, you can present the body plot just to justify that you think the circuit is low pass ke, high pass filter ke, band pass ke, band stop pass ke. Okay, so from here the bonus is at the bottom. There are two parts, so two capacitor in the feedback and in the input. So from there you can guess now what kind of filter is that. But until you simulate it, then you know what exactly whether. So this bonus part is, as I said, just for you all to experience the dealing with active filter. The manual and simulation detail will be from your main task lah. So this one is only a short simulation only. Okay. Any other question?
Doktor,
Yes.
kita orang dua-dua kena hantar report tu ke seorang je?
Satu saja.
Satu je.
Satu group satu. And okay, in front of the cover, report cover, you boleh identify lah task apa yang student 1 buat, student 2 buat. You can list that. So for example, manual analysis, simulation and discussion, so that I know contribution, who is contributing on which part. Or you can also put doing together all parts pun boleh. At least the reason that I want you all to identify who is doing what, so that between the two of you, you dah ada apa agreement lah. Your friend is going to do this part, you yourself is going to do another part, ataupun both buat sama and then discuss the results pun boleh. Okay, so at least you have mutual understanding. Okay, I will stop recording.